Hey everybody, this is Mr. Walsh, and today we're going to talk about the history of chemistry. And in in today's video, the history of chemistry is going to consist of two different parts, or two different things that were developed throughout the years. The first one is kind of the history of atomic structure, or what an atom looks like. And the second one is kind of the development of the periodic table. Okay. And to give you an idea of maybe the way to keep track of this stuff, okay, I have a sheet here that for my students, that's how it's going to work. But, I would write down the person, the year, and what they discovered that was important. Okay, some keywords, and then if there was an experiment that was named or something that was important, then you can put that in this box over here. The chemistry actually began back in ancient Greece, is where it's kind of credited for its beginning. And so there was this guy named Democritus who was around 400 BCE, and he was a philosopher. Okay, and so this philosopher, he came up with a thought experiment, and he said if we have drops of water, okay, and those drops of water are cut in half, and then we take it and cut in half again, then and again and again and again and again, and eventually we're going to get down to a part of water that can't be split anymore. Okay, and so what he called that was atomos, or that's, I think, Greek for indivisible, okay, or undividable. Okay, so he was really this philosopher that was like, there's got to be some smallest part to matter, to in this case a water droplet, that can't be divided anymore. Okay, and then a little bit later, Aristotle comes along, and he was also a philosopher. Aristotle was much more famous than Democritus was. He was the most popular person at the time in philosophy. He had it in with Plato. He knew all this stuff that was going on, and in a lot of ways, Aristotle was great. He knew a lot of good things, but he came up with this idea. He's credited with the four elements. So, earth, air, fire, and water. Okay. And so because he was so popular, these four elements became the standard. Okay. And we know now that this is wrong, that Aristotle had it all wrong from the beginning, and that Democritus was right. But because Aristotle was more popular, okay, he's the one that everybody went with and said, oh, Aristotle, must be the way that it works. But it's not. Okay, fast forward to 1650-ish. Okay, Robert Boyle is kind of credited with modernizing, or making chemistry a little more modern through what we call an experimental approach. Okay, and so what we mean by experimental is that he measured things carefully, and he would repeat experiments to make sure that he was getting accurate results. Okay, and so he would do this, and this was in the 1650s. Let me just tell you that, in the 1650s, we have not hit the Industrial Revolution. We don't have technology, so this guy's using ancient ways to measure things, and it's pretty impressive. Okay, so he worked with gases. So he did gas laws. Okay, we're going to actually come back to him later on in the unit. We're going to have Boyle's Law. Okay, I'll write that down. Boyle's Law. Okay, and so, but again, he's credited with kind of modernizing chemistry and maybe even science because of that. And notice we haven't gotten to the periodic table yet. Before we get to the periodic table, we have to talk about John Dalton. John Dalton in 1803, this guy's a teacher, okay? Not a college professor, he's a teacher, okay? He's in England. And he decided that, or not decided, but during his research, he realized that the atomic theory of matter is where it is. And so remember that Democritus came up with atomos. Well, he decided that atomos was the right place to go. So he came up with these 4 points to the atomic theory, and they're probably the basis of everything that we do in chemistry. So these are very important. Okay? And so what we know is that all matter is made up of tiny indivisible particles called atomos. Now this particular thing is incorrect. We know now that we can divide atoms into protons, neutrons, and electrons. There's a symbol for each of those. But at this point, we called them atoms, okay? And they were not divisible back 200 some odd years ago, 220 years ago. Okay, and so here the atoms are the same elements are the same, different elements are different, and so this is kind of the anti-alchemy clause. Okay, remember that alchemy. Okay, alchemy led into chemistry, and one of the biggest things that in the Middle Ages, when alchemy wizards and warlocks were around, one of the biggest things that people wanted to do is called transmutation. Okay, and they wanted to take lead and they wanted to turn it into gold. And so this clause is the anti-alchemy clause, where atoms of the same elements are the same, lead is lead, different elements are different. Lead can never be gold, gold can never be lead. Okay, so he was debunking anybody that was still around trying to do this. Okay, another thing that he could do, that he realized that there was some people doing research around this. Okay, atoms cannot be created or destroyed. Okay, they only are rearranged. And so this is the law of conservation of matter. Okay, and so this is still valid today. Okay, and so is this one. Okay, this one has changed. Okay, but the law of conservation of matter just says that atoms are rearranged in a chemical reaction and not destroyed or even made. Okay, and remember, chemical reaction from last unit, this is the same way as saying a change, chemical change, right? Okay, and the last one that John Dalton came up with was atoms of elements can be combined with different elements in whole number ratios. So the idea here is that you can have water, the ratio of water is going to be H2 to O, there's a 1 there. It's always going to be 2 to 1. It's never going to be H1.7 to O.3 or something like that. Okay? Or water is not H2O2. It's even though that's a whole number ratio. Okay? This is a different thing. This is water, and this is hydrogen peroxide. Okay? Okay. So John Dalton is the father of modern chemistry. That's kind of how we refer to him, because he put together the atomic theory of matter in 1803. And so now that we have an idea that there are elements and there are atoms, now people want to put the atoms and elements together. So we have this guy, the first attempt at kind of organizing these elements was this guy, Wolfgang Johann Dobereiner, And he found out that there are these things called triads, the prefix tri meaning 3. Okay? And what he realized that is if you take elements like lithium, sodium, and potassium, I'm going to make that a little bit bigger here. Lithium has a mass of 7. We could figure out the mass, and realize we're figuring out the mass before we have the instruments to actually measure these things. Like, they were calculating mass pretty well. So anyways, and so lithium and potassium have a mass of 7 and 39 respectively. When we add those two up, you get 46. You take the average, divide it by 2, that's 23. And this is a triad where the lighter one and the heavier one, when you average them, they get the middle. The problem with triads, okay, the problem is that there was only, even though there was about 60 elements, okay, there was about 60 elements, there was only about I think that there was like 10 triads, okay, give or take. There may be a few more, a few less. So that means that only half of the elements were fitting into triads. So this was a valiant effort to to organize the periodic table, but it really wasn't working because it didn't fit for all of the elements. And we wanted to try to figure out a way to get all of the elements organized into something that makes a lot of sense. Okay, and so then John Newlands comes along in like 50 years later, a little less than 50 years, and he comes up with this idea of octaves. And if anybody's musical, you know that that's 8 elements. Okay, and you can see here, we have do, re, mi, fa, sol, la, ti, and then do is over here, but then we come back around. And so the idea here is that elements were arranged in these octaves. But again, same thing with Dobereiner, is that they didn't all fit into the octaves. You can see here's an octave that has 2 elements. Here's an octave that is missing stuff. And it's like the 8th one is kind of, we're relying on coming back here. Notice elements like helium, neon, argon, the noble gases, they haven't been discovered yet. Okay, so again, the problem with octaves is not all the elements fit into the idea of 8 going across. So we're really trying to figure out how are we going to get a table that has all the elements organized correctly. So this is where Dmitri Mendeleev comes into play. He is the father of the periodic table, and he developed and understood this thing called periodic law, where the elements are grouped using their chemical and physical properties. Okay? And so he said that elements, like everything here, are going to have a very, very specific type of reactivity. Okay? These guys, helium, neon, argon, have now been discovered. Okay, and now they get put into the periodic table in a place where they're all kind of together. Fluorine, chlorine, bromine, that sort of thing. These guys are all grouped together because they have similar chemical properties. That's what we mean by periodic law. Okay, so when we look down each of the columns on the periodic table, we can say, oh, these elements kind of have the same properties. Okay, these metals here all kind of react with water. Okay, these metals here form bases when mixed with water, so they get slippery, and it's just kind of a yucky thing. Okay, and the very, very clever thing about Mendeleev's periodic table is that he left spaces for the elements that hadn't been discovered yet. Okay, and that is important to realize, is that those spaces were left in the periodic table. Okay, fast forward about 30 years. Now we're going back to the atom. We have a periodic table now that seems to work, and now we're going to the atom. And so J.J. Thomson here, he discovers the electron. Okay, and so he realizes that an atom, Dalton's atom, was kind of like this was a like a marble. Okay, and some people will say that Dalton came up with the atomic marble theory. Okay, what J.J. Thomson decided when he did his cathode ray tube experiment, that's the important experiment here, is he came up with the plum pudding model. So he said that, yes, there's this sphere, but inside there are these negatively charged electrons that can be removed. And it's called plum pudding because he was English, but what you can think about is if there was like a blueberry muffin, the cathode ray could pick out the blueberries out of the blueberry muffin. Okay, and so he was saying that the electrons, which we know are negative, was in this kind of positive goo of batter that was the muffin, and the negatively charged blueberries, and he could pick them out. Okay, so we kind of moved from the atomic marble to what the English would call plum pudding, or maybe we would call a blueberry muffin. Now we start getting really good, because not only are people starting to learn more, but we also now are starting to develop the technology. Okay, so as we develop the technology through history, we are able to get more and more experiments, better and better experiments, to help determine the structure of an atom. Okay, and so what Rutherford realized through his gold foil experiment, that's the important thing, is that there was a nucleus. So we have Thomson with the plum pudding model, okay, where you had these negatively charged atoms in the positively charged batter. Well, what Rutherford realized is that there was this little tiny positively charged nucleus with electrons that kind of floated around the nucleus, and there was a whole bunch of empty space between the nucleus and what was going around. Okay, and so the gold foil experiment in 1909 really was groundbreaking, and his interpretation of it to get the nuclear model is really important. Millikan came along, and Millikan is this guy that's like, this is all he ever did. He did the oil drop experiment. Okay, and the reason why he's important is because, again, technology is getting better and better, and so he put these little oil drops into a container, and then he made them hover by changing the voltage between the plates. So this drop here would come down through this container, then it would come through, and there would be one drop here. You'd change the voltage until this drop would be suspended. Okay, and then he could measure what that voltage was. Eventually, through this experimentation that he did over and over and over again with accurate measurements, like Robert Boyle, okay, he determined the numeric charge. He quantitatively came up with that number. Until this point, okay, when Thomson did his electron experiment, he just discovered there was an electron. This guy, 15 years after J.J. Thomson, he discovered the number of the charge. In the same year, Moseley discovered, did a lot of work with the nucleus. Okay, Henry Moseley was doing work with the nucleus, and when he was doing work with the nucleus, he realized that there were protons, particles. Okay, and so the protons then became the atomic number. So what he did is he put the finishing touches onto Mendeleev's periodic table, and Mendeleev used atomic mass to do that's all he had. Okay, 50 years before, he was just using atomic mass. Moseley comes along and he uses atomic number and gets rid of using atomic mass as the way to organize elements, and this really clarifies the periodic table. Okay, and that was, over 100 years ago that we really have the periodic table that we have today. Okay, we didn't have all the elements in 1913. We only had 93 elements, but it was still the way it worked. So Moseley helped with not only the atomic structure, understanding atomic structure, but he also helped organize the periodic table. Bohr helped create what we call the Bohr model, Niels Bohr, in 1921. Okay, the Bohr model is important because, again, if we're talking about the development, we had Thomson. If we're talking about the development of the picture of an atom, okay, Thomson had marbles, and then Rutherford came up with the nuclear model. Thomson had plum pudding, right? It was Dalton that had the marbles. Okay, and so now we have this, and then the electron around the outside in this thing. Bohr, he realized that the electrons are in specific areas around, they orbit much like the solar system, is what he said. Okay, so this is like the solar, we sometimes call this the solar system model. Okay, is that that electrons here have a set energy, and Bohr said, because they have a set energy, they must be a set distance from the nucleus. So they orbited around this. Okay, and so Bohr kind of clarified what Rutherford started, and so now we really have a decent picture of what an atom looks like. Erwin Schrödinger, okay, and so I think he was in the in that movie Oppenheimer. Okay, there was a nucleus, but instead of having orbit like the Bohr model, he said that electrons can move anywhere within that orbit. And so when electrons are moving around, it creates this cloud of electrons. And so he did a lot of crazy calculations to figure out how electrons move. And so he realized that electrons move randomly and not in a set pattern like Bohr. This thing that happened in 1932 for this presentation is Chadwick had the beryllium experiment. Okay, and what he did with the beryllium experiment is he discovered a neutron. A neutron wasn't discovered until 1932. Okay, so that's less than 100 years ago. Okay, we didn't even know all the parts of a nucleus. Nucleus up until this point was positive. Now we know that a nucleus has neutral charge things, and that the electrons are floating around in this cloud. Okay, and so it wasn't until James Chadwick came along that we understood what that the nucleus had this other atom. We kind of knew it, but he was the one that actually discovered it. So, okay, there you have it. Longest video I'm ever going to make for for you guys, but go through it. Feel free to pause it and get all the information you need. Okay, everybody, have a great day.